Welcome back to your favorite stats class of all time. I am your humble instructor, Chad Bemis. All right, today we're going to talk about continuous probability distributions. Module 8.1. All right, so probability models with discrete and continuous numbers. So we need to talk about what that means. So discrete versus continuous. All right, so discrete numbers are what we normally think of as counting numbers 1, 2, 3. So a discrete variable represents data that is countable. So the number of household pets in a given population. Maybe one person has 4 pets, another has 2, another has 10, but nobody has 2.8 pets. What is 0.8 of a pet, right? So you either have a pet or you don't. So we tend not to use fractions or decimals, but an exception to that rule would be money. Obviously, $2.56 is a decimal amount of money, but remember that means 256 pennies, right? So that is a countable. That's a whole number of pennies. So when we talk about discrete data or discrete variable, we're looking at things that can be counted, right? That can be counted. On the other hand, continuous means that it's basically could represent any number on the number line. So measurements, right? Could be whole numbers, fractions, decimals. So, could we more, a lot of times when we give measurements for, let's say, construction, we go down to the 16th of an inch, right? So 5/16 inches. But could we break that down further, right? Could I say could I go down to 5/32? Well, yeah, it may not be represented on the ruler or on the measuring tape, but it can be. So if we convert that to decimals, it can go down even more specific. So anyway, so think about any possible decimal that can work. That's continuous. So an example of continuous data might be miles driven in a car. Even though your odometer might say, 2.8 miles, you've gone 2.8 miles since you left home. Remember that 2.8 could be rounded from 2.82, which could have been rounded from 2.8 to 4, and so on and so on and so on, right? So these are continuous numbers because it's could be representing anything on the number line, not just whole numbers. Okay, so if we look at the temperature in Fahrenheit, so the temperature in Fahrenheit of various emergency rooms throughout Washington. So would this be discrete or would this be continuous? Well, remember temperature, even though normally we only round to the nearest whole number, temperature can be any number. So this would be continuous. Next example, the number of foreclosures on houses in the Pierce County area. Or you could use the word homes. Houses, homes. Doesn't really matter. This will be discrete because you can't have a half a house, right? Half a house or 0.2 houses makes no sense. The current mileage on a used car, or a new car for that matter. This will be continuous because, again, as we mentioned earlier, mileage can be broken down into more specific measurements. The number of planes landing at the airport, discrete or continuous? That's right, it's discrete. The number of peanuts in a jar, assuming that we're counting only whole peanuts. Once again, discrete. So yes, you could chop a peanut in half, but we're only considering it a peanut if it's a whole peanut. How about the weight of the same jar of peanuts? Continuous. All right, so when we talk about random variables, probability models or probability distributions, what we're talking about is a variable whose numeric value is determined by the outcome of a random experiment. So we're going to show an example of this in just a minute. Actually, it's an example that we've looked at before. So a random variable is usually denoted by x, y, or z. X is probably the one we're going to use the most often. Notice that it's a capital X. Okay? A probability distribution or a probability model is a table or formula that lists the probabilities for each outcome of the random variable x. This only works for discrete random variables. Because continuous, there's just too many to list, right? There's too many to list. So currently, we're specifically talking about discrete random variables, which, as you remember, are numbers that are whole numbers. May not have mentioned this 0, but it is possible to have 0 planes sitting on the tarmac, right? So 0 does count as a discrete number. All right, so the way we're going to set this up is actually very similar to a frequency distribution, which, remember, also gives us pictures of data such as histograms and things like that, relative frequency histogram, or plain old frequency histogram. But in this case, we're going to have probability substituted for frequency. And by the way, and make sure that when you're creating this probability model or probability distribution, that the sum of all the probabilities must equal 1. In other words, 100%. So we're going to create a probability model for the rolling of 2 dice, where x was the sum of the 2 dice. So we talked about this in a previous video. And remember, we drew diagonals. And the diagonals represented the sum. Right? This diagonal represents 2, the sum of 2, because 1 plus 1 is equal to 2. The next one is 3. These are all worth 4, and so on. Seven, 8, 9, 10, 11, 12. So the possible sums that we have for values of x are 0 through 12. And then we can ask ourselves, okay, what is the probability of each of those x values? The probability of each of those x values is determined by the number of ways, let's say for 2, for example, the number of ways that we can get a sum of 2 out of the 36 possible tosses of 2 dice. Well, all you have to do is just count how many of them there are. So in this case, it's just 1. So 1 out of 36. And then count how many have a sum of 3, right? Excuse me, this is incorrect. 2 is the minimum that you can get because 1 and 1 is the smallest amount of smallest amount that you can get on the dice. So this is 1/36. This is going to be, there's a possible of 2 out of 36 that add up to 3. There's 3 of them that add up to 4. 4 of them that add up to 5. 5 of them that add up to 6. 6 of them that add up to 7. Then we're back to 5 that add up to 8, and so on. And finally, for 12, there's only 1, right? So this is the probability distribution for the sum of the 2 dice, right? 2 through 12, right? So remember that we have to determine if this counts as a true probability distribution, the sum of all of these fractions has to be 1. So since they all have the same denominator, we can add the numerators together, and if the sum of the numerators is 36, then the sum is 1, right? So if I add, excuse me, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. So that's the sum of all of the numerators here, 36. And since the denominator is 36, I divide by 36. And there it is. So we've verified that the sum of all the probabilities is 1. Okay. So here it is horizontally, right? Same thing. All right, so here we've got another example. This table is a probability model or probability distribution for the number of days that a randomly chosen patient says that he or she has worked out. Excuse me, in the last 7 days or in the last week. Excuse me. So where an x is equal to 0, that means that the patient worked out 0 times. So the 68 means that 68% of the patients that were surveyed didn't work out at all that week. 8% of the patients worked out 3 times, 4% worked out 5 times anyway, so and so on. So I have to make sure that this is, in fact, a probability distribution where x is the number of days that the patient had at least one workout. So, of course, what I would do is add those decimals up. So I would say 0.68 plus 0.05 plus 0.07 plus 0.08 plus 0.05 plus 0.04 plus 0.01 plus 0.02. And those should add up to 1, which they do. So this is a probability distribution model. All right, so let's ask a question about it here. So the probability P of x means that the probability that a random patient has worked out that many days. Okay, so again, 68% of the sample patients worked out 0 days per week, and that's represented by this information here. So we've already verified because the sum of all the px's is 1. All right, so in words, what do we mean when we say x is, this is a greater than sign, by the way. X is greater than 7. What is the probability that x is greater than 7? So there's 2 questions being asked, right? There's 2 questions. So first question is, what does x is greater than 7 mean in words, right? What does this mean in words? The second question is, what is the probability that x is greater than 7? So in words, what this is saying is that the number of days that the patient worked out was more than 7. But that's in a week. So there are not more than 7 days in a week. So the probability that x is greater than 7 is 0. Because 7 is the number of days in a week, as we said. Express the event worked out at least 1 day in terms of x. That would be at least greater than or equal to 1. What is the probability of this event? So the probability that x is greater than or equal to 1. Well, think about what it means at least 1 day. Sort of analogous to asking the question, are you at least 21? Means that you can buy alcohol or that you can gamble, right? So at least 1 counts 1. It counts 2, 3, 4, 5, 6, and 7. But that's a lot of numbers to add up. So instead of calculating that directly, we could say, well, it would be the complement of the event that they didn't work out at all. So 1 minus 0.68 would give me 0.32. So if I was to add up all of these numbers, not including the 0.68, I should get 0.32. So in other words, 32%. So what we're saying is that the probability that a randomly selected person in this model has a 32% probability of working out at least one day. Or the other way to say it is 32% of the respondents or of the patients worked out at least one day. Sorry for the messiness of the writing there. All right, continuous probability models do not look the same as discrete, as we mentioned earlier, because there's just too many numbers to list. It's impractical or impossible to display it in a table. There's often an infinite set of possible outcomes, and we can't list that many. So let's say we're going to generate some random numbers, okay, from a random number generator. So you could be using a computer, you could be using a calculator, whatever. We're using 7 decimal places, and we're going to go from 0 to 1. All right, so here's 5 random numbers that the computer could have picked. And you can do this on Excel, by the way. Excel will generate random numbers for you. Okay. Our sample space is now basically the entire interval of numbers. Technically, it would be all of the numbers that have 7 digits from 0 to 1. So we could technically list them out. 0.0000000, 0.0000001, and so on, all the way up to 1.0000000. But you can imagine this would take quite some time to list and is very impractical. Okay, so what we have to ask ourselves is, well, what's the probability of each individual number? Well, basically, the probability is either 0 or near 0 because there's so many of them, right? So instead of saying what's the probability of an individual number being selected, so let's say you selected the number 0.1, 2, 3, 4, 5, 6, 7. If I was to use Excel and I was to randomly generate a 7-digit decimal between 0 and 1, what's the probability that it would select that exact number? And of course, the answer to that is basically 0, right? So instead of saying that, we can use the words more than, less than, at least, at most. So this expression says x is between 0.3 and 0.8. In other words, the random number that the Excel generates will be between those two numbers. That we can calculate, okay, using what we call a density curve. In this case, we have what's called a uniform distribution, which looks like a rectangle. And the rectangle has an area of 1 because the sum of the probabilities is 1. Okay. So here's an example. What would be the probability that a randomly chosen number will be between 0.4 and 0.8? Between 0.4 and 0.8. And you could include the 0.4 and 0.8, or you could disclude it. It doesn't really matter. So the hint here is that we're going to use the rectangle that we talked about above to find that probability. All right. So what we'll do here is create a number line. Let me go back to the slide here. We'll create a, hang on. We'll create a y-axis, and we'll create an x-axis, where this is 0, and this is 1, and this is 1. So the distribution can be represented by this square. So sometimes it's a square, sometimes it's a rectangle. And remember that the x-axis is the random variable, which is the random number that's generated by the computer. In this case, it's between 0 and 1. And the y-axis is the probability. Okay, so what we're going to do is we're going to use a smaller rectangle to determine the answer to our question. So as you may recall, this is 0.5. We're looking for the probability that the random number generated is between 0.4 and 0.8. Okay, this is not exactly drawn to scale, but it doesn't really matter, because the point is, once you visualize the rectangle here, it's very simple to figure out the area, right? So it looks about half, maybe a little bit less than half of my overall area. Okay, but I can calculate it very simply. Remember that the area of a rectangle is the length times the width, or in this case, the base times the height. So what I have to do is calculate or figure out, either calculate or figure out, it doesn't really matter, the width or the base of the rectangle. Okay, and I have to figure out what the height of the rectangle is and just multiply those two numbers together. Well, the base is the distance from 0.4 to 0.8, which is 4/10, right? And the height of the rectangle is 1 because of that. So the area of the rectangle is the same as the probability that we're looking for. So this is an example of a continuous probability distribution. So that's the answer to the question. So the probability that the random number generated is between 0.4 and 0.8, and we could include those, again, it doesn't matter, is 40%. So it's a probability of 40%, because it's 40% of the overall area. Okay, we saw that slide already. Now let's take a look at figuring out what the probability of x is less than 0.4. The probability that x is less than 0.4. So let's draw that square again. There's 0.4. So that would be the probability that x is less than 0.4, or at least that would be the pictorial representation of it, right? So once again, I would need to use the area of this strip that I just drew, which is the base, which is 0.4 minus 0, which is 0.4, times the height, which is 1. Okay. Probability that x is less than, let's say, 0.9 would be, there's 0.9, would be all of that. So it would be 0.9 times 1, or 0.9. So there's a couple of different examples of how we could use the uniform. Coming up in a few different presentation, we're going to talk about the bell curve, or the normal distribution, which we have mentioned before. The normal distribution is not looking like a rectangle, so we have to use something a little bit different. The something that we use is called the standard normal curve. And there's actually a formula for it, but what we're going to use is the calculator. This is called x bar, the mean. So here, the uniform distribution, we just use rectangles to calculate the area, excuse me. Here we can use a table, or we can use the calculator, which is how we're going to do it. So another example, we did that already. Okay, another example is that we're going to take the sum of two numbers generated between 0 and 1. So, for example, if the two numbers were 0.5 and, let's say, 0.9, right? The sum of 0.5 and 0.9 is 1.4, right? 1.4, which is right about there, right? So again, the height of this is 1 because we need to have a complete area of 1. You may recall that, let me erase this. You may recall that the area of a triangle is 1/2 times base times height. Well, the base is from 0 to 2, which is 2, and the height is unknown, and we know that the area has to be 1. So 1/2 of 2 is 1 times h is 1, which means the height has to be 1. Okay. All right, so the question we can ask, what is the probability that the sum will be less than 1? So just like we did with the rectangles, this would be the probability, pictorial-wise, that the sum is less than 1. So we could either look at it and say, hey, that's 1/2 of the overall area, or we could say it's 1/2 the base, which is 1, times the height, which is 1, which still ends up being 1/2, so probability of 50%. And what's the probability that the sum is less than 1/2? Okay, less than 1/2. Well, here's 1/2, about right here. Again, not exact. Okay, the base, hopefully it's clear that it's 0.5. So the area of that little chunk is 1/2 the base. Now, the height, you can think about it for a second. Does it make sense that the height is 1/2 of the overall height of the triangle? Because of the fact that we're halfway between 0 and 1 here, we're going to be halfway between 0 and 1 on the height, right? Which tells you that the height is also going to be 1/2. And I believe that's 0.125, but let's double, oops, 0.125. Let's double check that. All right, so 1/2 times 0.5 times 0.5. Yep, 0.125. And that concludes the presentation.